The topic is Kubernetes cluster upgrade. Why we upgrade Kubernetes cluster, mandatory architectural prerequisites of Kubernetes cluster upgrade, and step-by-step upgrade process of self-managed Kubernetes cluster versus EKS in theory. Also, we will discuss managed services versus self-managed clusters. What is the difference between them? But before we begin, my name is Kaif Mohammad Khan. I'm a recruiter in the past. Now I've moved into DevOps from scratch. This is part of my transition series. If you are making the same switch, stick around. A Kubernetes cluster upgrade is the methodical process of updating a cluster's core system components from an older version to a newer version. Example, that is from version 1.35 to 1.36. Because Kubernetes uses a distributed client-server architecture, upgrades cannot be done all at once. They must be executed in a precise layered sequence to keep applications online and prevent version incompatibilities from breaking cluster communication. So Kubernetes cluster upgrade is a methodical process of updating clusters core system components from previous version to the latest version of it. Because Kubernetes is a distributed client-server architecture, the upgrades cannot be done all at once. It must be executed in precise layered sequence so that the applications are up and running and the updates of the versions does not cause breaking in the cluster communication due to the version incompatibility. So why we upgrade the Kubernetes cluster? Let's understand in the sense of business and technical triggers. The 1-year support window. The Kubernetes community only maintains the 3 most recent minor versions. Each version receives security patches and critical bug fixes for roughly 12 months. Running an unsupported version leaves the cluster exposed to unpatched vulnerabilities. API deprecations. Internal features and configurations like ingress or deployment schemas transition over time from version 1 beta 1 to version 1. Upgrades ensure the environment remains aligned with modern code standards before obsolete APIs are completely removed from the binaries. Feature availability. Minor releases bring core structural upgrades such as native CG group version 2, resource handling, scheduling performance optimizations, and enhanced encryption mechanism. First, why we upgrade Kubernetes cluster? It is because Kubernetes community only maintains recent minor 3 versions of the current update. Each version receives security patches and critical bug fixes for roughly 12 months. Meaning, if you are in the Kubernetes latest version right now, it would take nearly 1 year for it to get maintained by Kubernetes community, and after it would be unsupported version that leaves the cluster exposed to unpatched vulnerabilities. Second is internal features and configuration such as ingress or deployment or other schemas transition over time, that is from, for example, version 1 beta 1 to version 1. So upgrading it ensures the environment remains aligned with modern code standards before obsolete APIs are completely removed from the binaries. Minor releases or releases in the Kubernetes for upgrade brings core structural upgrade such as native CG groups, version 2 resource handling, scheduling performance optimizations, and enhanced encryption mechanisms. So each update or upgrade that the community of the Kubernetes provide brings core structural upgrades like native resource handling, scheduling performance optimization, and enhanced encryption mechanisms. Now, mandatory architectural prerequisites of grading Kubernetes cluster. Before altering a cluster, we must validate that the components conform the official Kubernetes versions queue policy. If this mathematical versions constraints are violated during planning, internal components will reject the communication, breaking the cluster. So, Kubernetes cluster upgrade has prerequisites, meaning before we even upgrade, there must be certain standards or certain rules or certain SOPs you must follow in order to have successful upgrade of Kubernetes cluster. If we miss out on such steps, there exists a strong possibility that internal components will reject communication, eventually breaking the cluster from working. So it must conform or follow to the official Kubernetes versions queue policies. A, or the first is the control plane rules, that is Kube API server. The Kube API server acts as the definitive version anchor for the entire cluster. In high availability HA environments with multiple master nodes, our active Kube API server instances can differ by a maximum of one minor version. All the other control plane components, Kube Controller Manager, Kube Scheduler, must match or be at most one minor version older than our newest Kube API server. They can never be newer. This means that in high availability environments that has multiple master nodes, our Kube API server instances can only differ by maximum of one minor version. Meaning if Kube API server is at version 3, high availability HA environments with multiple master nodes must be at least at version 2, not version 1. And other components in control plane like Kube Controller Manager, Kube Scheduler must match or be at most one minor version older than our newest Kube API server. Meaning if the newest Kube API server is at version 3, it must be at least or at most one minor version older, that is version 2. It can't be less than that. B, that is the node rules, kubelet and kube proxy. The -3 boundary, the local agent on worker nodes kubelet can be up to 3 minor versions older than the Kube API server. The overskew trap, worker nodes can never run a version newer than the Kube API server. If we have a control plane at version 1.34 and we attempt to connect a node upgraded to version 1.35, it will be rejected. Upstream core constraints, the administrative CLI tools kubelet is supported only with one minor version plus /-1 of Kube API server. Now for kubelet, it can be up to 3 minor versions older. Meaning if Kube API server is at version 5, kubelet can be at version 2, not less than that. And worker nodes can never run a version new or latest than the Kube API server. For example, if the control plane is at version 1.34 and we attempt to connect a node that is upgraded to version 1.35, it will be rejected. And the administrative CLI tool, that is the kubelet, only supports one minor version than the Kube API server. If Kube API server is version 5, it must be at least version 4, not less than that. So local agent on worker nodes kubelet can be up to 3 minor versions older than the Kube API server, and worker nodes can never run a version latest or new than the Kube API server. And administrative CLI tool kubelet supports only one minor version than Kube API server. C, system and environment readiness check, single version jump only. You cannot skip minor versions, for example moving straight from version 1.33 to 1.35, that is prohibited. You must upgrade sequentially, that is version 1.33 to version 1.34 to version 1.35. etcd state backup. We must take an explicit standalone snapshot of the etcd distributed database. If the control plane binaries corrupt data during database schema migration, this file is our only path to recovery. Disable swap memory. Ensure swap remains completely disabled across all node operating systems, as kubelet binaries will fail to initialize if swap space is active. Container runtime interface, that is CRI. We must verify that the underlying runtime container engine, for example containerd or Creo, is validated for compatibility against the target Kubernetes release version. So we cannot skip minor versions, meaning we cannot go from 1.33 version and directly to 1.35 version. We must upgrade sequentially, that is 1.33 to 1.34, then to 1.35. For extra safety of backup, we must take standalone snapshot of etc distribution database. So if the control plane binaries corrupt the data during database schema migration, this file is the only path to recovery or to recover those data in the etcd. Although in the newest versions of Kubernetes, swap memory being active or disabled doesn't affect the upgrade process, meaning it will not affect the binaries to initialize. But for our convenience or to be on the safe side, we can completely disable swap memory across all node operating systems to avoid kubelet binaries to fail to initialize if the swap space is active. Also, we must verify that underlying runtime container engine, that is CREO or containerd, is validated and it is compatible against the newer version or the latest version we are targeting to upgrade for. So that was about the prerequisites of Kubernetes cluster upgrade or update. Now let's understand the step-by-step upgrade process. First is self-managed. Self-managed here simply means we are the owner and we manage all the services and we are responsible for its working and maintenance. Comparing it with the EKS or other cloud provider services. Self-managed means we are managing our own cluster by ourselves and we are building it. So the upgrade flow strictly is from top to bottom. That is control plane nodes first, then worker nodes. For this we upgrade the tooling and target verification, that is the step 1 admin system, and hold and upgrade the package manager tools kubeadm on the primary control plane host to the precise target patch version. We must run the kubeadm upgrade plan to execute automated pre-flight checks that verify cluster health and fetch available target components. So step 1 is admin system, where we aim to update the kubeadm, which is the package manager tools. We upgrade that on the primary control plane host to the precise target version we are aiming for. To do this, we run the command kubeadm upgrade plan to execute that automated pre-flight checks that verify cluster health and fetch available target components. Step 2, that is in the control plane node 1, we upgrade the primary control plane. We execute the command kubeadm upgrade apply version which we are aiming for. This pulls the target version images and automatically updates the static pod manifest for the core system components kube API server, kube controller, manager, kube scheduler. This means that we apply the command kubeadm upgrade apply with the version we are aiming for. This pulls the target versions images and automatically updates the static pod manifest for the core system components, that is kube API server, kube controller, manager and kube scheduler, meaning it upgrades or updates it. Now as we updated control plane node 1, in step 3 we aim for upgrading or updating highly available nodes, meaning upgrading secondary control plane instances. For clusters running multiple master hosts, we log into the remaining control plane nodes one by one and execute kubeadm upgrade node. This updates local configuration without reinitializing the cluster data pool. So as we did the update or upgrade in the primary control plane node 1, in the step 2 we have applied the command kubeadm upgrade apply with that version. So we do this command for single primary control plane node 1, and with the rest of the other nodes present in that same control plane, we don't need or we don't perform that same command. Instead, we perform the command that is kubeadm upgrade node, which would mean that this command would upgrade that to the upgraded version which we did for the initial first node. We do this command for each nodes or instances in the control plane present. Now step 4 is master node agents, that is to update local control plane kubelets. To do this, we drain the master nodes, we update their host level kubelet and kubelet package binaries to match the new version. We restart the system service via systemctl and uncordon the nodes. So here the drain of the master nodes and then we updating it means that updates or upgrades cannot happen when there is an active application running on that nodes. So we can either create a fresh node and perform update on it, or either we can drain or evict that node to perform the update or upgrade by performing the command kubeadm upgrade node. Now for step 5, we do the same by draining the worker nodes by this command. This safely evicts active application pods that triggers the scheduler to recreate them on other healthy nodes to maintain zero application downtime. The purpose is same. The upgrade or update cannot cannot be done when an application is running or when the application is running in the pod. To do that, we drain or empty that pod and we perform the upgrade on it, or either we can create a new node and perform the upgrade or update. After this, there is step 6, where we upgrade the worker node components. We log into the cleared worker node and we upgrade it packages by performing kubeadm package, run kubeadm upgrade node, and we upgrade the host operating systems, kubelet and kubeproxy packages, and then we restart the services to initialize the updated node daemon. So after draining and evicting the pods and emptying the nodes, we perform the command to upgrade the kubeadm package, that is run kubeadm upgrade node. It upgrades host operating systems, kubelet and kubeproxy packages, and after it is done, we restart the services to initialize the updated node daemon. After step 6 is done, we perform step 7, that is the re-entry of restoring the worker node to service. We perform kubectl uncordon with the node name to mark the node as scheduling ready. This ensures that the scheduler distributes the workload back into the upgraded or updated host which we have done, and we repeat the step 5 through 7 iteratively across all remaining worker nodes in the cluster infrastructure. So we perform the drain by emptying the node so it is empty and it is fresh, and it mimics that it is a new node for making the upgrade successful. If the node has application running, the upgrade or update is affected or is manipulated and it cannot be successful. So we drain it. Then we log into the cleared or the drained worker node or the node, and then we perform the run kubeadm upgrade node to upgrade its kubeadm package, which upgrades its host operating systems, kubelet and kubeproxy packages. Then we restart the services to initialize the updated node daemon, and then we perform kubectl uncordon with the node name to mark it as scheduling ready, meaning to make it ready. So the scheduler will distribute the workload across and back to the upgraded or the new host, and we repeat the steps on other nodes in the cluster infrastructure. So that was about self-managed clusters. Now for managed, that is EKS in AWS or other service providers. Step 1 is EKS control plane upgrade. AWS hosts the control plane components, that is Kube API server, etcd, Kube scheduler inside an isolated AWS managed VPC. Our application continue to run undisturbed while AWS swaps these underlying servers out in the background. So AWS is a cloud provider and it hosts the control plane components, that is Kube API server, etcd, Kube scheduler inside an isolated AWS managed virtual private cloud, that is VPC, and our applications continue to run undisturbed while AWS does the heavy lifting of swapping these underlying servers out in the background. First is pre-flight validation. We scan for all running application deployments to ensure they are not using APIs deprecated in the target version. Then we perform or to trigger the API update. We execute the upgrade request using AWS CLI or Terraform. We can only move up by one minor version at a time, which is like the prerequisite step we discussed. For example, if it is 1.31, we must do it 1.32, not 1.33. And the command to trigger the master control plane software upgrade is AWS EKS update cluster version with the region US East 1. We can do it with other which you have specified, and the flag name, that is production cluster, or it can be anything which you have named, and the flag is Kubernetes version that we are targeting, 1.32 in this case. Then blue or green follower. AWS spawns fresh control plane nodes running version 1.32 alongside our current nodes, synchronizes the database, transparently reroutes internal cluster traffic to the new instances, and removes the old nodes. So in this, AWS spawns fresh control plane nodes that runs with the version which we have specified for the upgrade, that is 1.32, alongside our previous old version nodes, meaning both of them would be present. Then it synchronizes all the database and information, and it transparently reroutes the traffic to the new instance with the new version of 1.32, and it removes the old nodes. It happens quickly in the background and it almost gets unnoticed, but this is what happens in the background. And next is verification. The cluster transitions out of the updating state, then we verify the readiness. The command for checking or the verification is AWS EKS describe cluster with the flag with the region US East 1 in this case, and flag name with the production cluster name. It can be anything which you have named. And the next flag is query, that is quotes cluster dot status quotes. So we wait until it returns active as the status. Now for step 2, managed node group upgrade, that is data plane. Once the control plane status changes to active, we upgrade our worker nodes pool. EKS managed node groups automate this via a rolling search upgrade strategy to maintain zero application downtime. So we can understand control plane as the root folder, and other aspects, that is worker nodes or master nodes, are the sub-root or subfolders inside it. So in that case, we first need to update or upgrade the control plane. We have done that in the step 1. So now after we observe status change to active, then we can upgrade the worker nodes pool by this command, that is AWS EKS update node group version with flag of region US East 1, cluster name flag with production cluster, flag node group name, that is primary node pool, we can name it anything, and the target version, that is Kubernetes version 1.32. So EKS managed node group automates this via rolling search upgrade strategy. This maintains zero application downtime. This is the command to execute it, or else there is the UI thing you can do in the interface of AWS as well by performing the upgrade. So we perform this after we have checked the status to active. Then launch upgraded instances, that is infrastructure scale up. The underlying AWS autoscaling group provisions a new EC2 instance built with the newest pre-baked EKS optimized AMI matching the target version. So after we successfully perform the step 2, the AWS autoscaling group provisions a new EC2 instance with the newest pre-baked EKS optimized AMI matching the target version which we have specified. Then for the second thing, cordon and drain old nodes, which is graceful pod relocation. Once the new nodes are registered as ready, meaning in the new instance with the latest or targeted optimized AMI matching version, once it is registered as ready, AWS will automatically trigger the cluster drain on old node, shifting pods smoothly onto the new hardware. Third is termination or terminating the legacy instances, which is resource reclamation. When the old worker node instance is entirely empty, AWS safely terminates it. This loop repeats one by one until our entire fleet is refreshed. So there would be new node creation, or that would be marked as ready, which would trigger AWS to perform drain on old nodes with old versions, then shifting those into the new upgraded nodes. And when the old instances or nodes are empty, AWS will safely terminate it. This loop will continue until our entire fleet is refreshed. Now step 3, that is EKS managed add-ons upgrade. System critical utilities running inside the cluster must be updated immediately after the node pools catch up. Upgrading them out of order can disrupt pod-to-pod networking or DNS resolution. So after the step 2 is done, where node pools are upgraded or updated and old ones are drained and deleted, some critical utilities running inside the cluster must also be updated immediately, meaning those are mandatory add-on upgrade lifecycle, which is in this order. First is VPC CNI, that is networking plugin. Second is core DNS, which is internal cluster DNS. Third is kubeproxy, network routing rules. And if we upgrade them out of the order, that can disrupt pod-to-pod networking or DNS resolutions. So first, we retrieve target patch versions. We query the AWS API to locate the valid version strings specifically compatible with our newest or the new cluster version. The command for it is AWS EKS describe add-on versions with the flag region and the region name US East 1, flag with the version Kubernetes 1.32, and the flag add-on name code DNS, and the query flag with add-on bracket dot add-on versions (add-on version). This command would look up the matching add-on image versions available in our specific region. Then second, we perform execute add-on upgrades to update our cluster components sequentially using the appropriate version strings. That is the flag resolve conflicts reserve flag, which ensures any custom configuration adjustment which we have done to the system deployments remain intact. The command is AWS EKS update add-on flag with the region cluster name flag with the production cluster name, add-on name flag with its name, that is the add-on VPN CNI, add-on version flag with the version, for example version 1.19.0, EKS build 0.1 flag resolve conflicts reserved. So the preserve flag ensures any custom configurations which we have made to the system deployments remain intact. So we perform this command changing VPN CNI to core DNS and its add-on version, and same for kubeproxy with add-on name kubeproxy and its add-on version. So after the add-ons are upgraded, we verify it. So verification confirms that our platform add-ons successfully update and converge back into a stable state. We verify that all components have converged back to an active state by this command. AWS EKS list add-ons with the flag region US East 1 flag cluster name production cluster flag output that is stable. So we check the status if it is active not. So that was about step-by-step process of cluster upgrade. First we have discussed for self-managed and then for EKS, that is AWS cloud provider. Other cloud providers would have some different commands. Now finally we will discuss what is the difference between managed services versus self-managed clusters. We must know that operational workload changes dramatically depending on where our cluster is located, meaning feature or responsibility of control plane lifecycle. Self-managed kubeadm or bare metal, it is manual. We execute all system package upgrades, image pulls and master configuration adjustments, whereas for managed AWS EKS, Google GKE or Azure EKS, it is automated. The cloud vendor performs rolling upgrades of the control plane nodes using a single console click or API call. So as I mentioned before, like in manual or self-managed nodes, we perform all the upgrades manually, as we are claiming to be the owner or isolated ownership of that cluster. That can be bare metal. Whereas for managed AWS EKS or other providers, it is automated by single click or API call. For etcd management in self-managed bare metal, it is manual. We handle snapshot, storage limits and database schema compatibility checks. Whereas for managed AWS EKS, Google GKE or Azure EKS, it is abstracted, fully handled by the cloud platform. Users have no direct access to etcd. Now for API auditing in self-managed, it is manual. We must check and fix deprecated manifest using tools like Pluto or kubectl. Whereas for managed AWS EKS or other providers, it is shared. The provider alerts you via dashboard about deprecated APIs in use before letting us upgrade. Worker node upgrades in self-managed, it is manual. We handle all the individual operating system package upgrade trains and uncordon processes. Whereas in managed AWS EKS or other providers, it is semi-automated, meaning we trigger a rolling update of a node pool and the cloud orchestration automatically brings up new instances, drains old ones and tears them down. So in short, for self-managed, we manage all the heavy lifting, whereas for managed, that is cloud providers, AWS or others, it is automated, shared, and we have to do less of the work. Whereas for self-managed, we have the privacy and compliance. For AWS, it is still safe and private, but it is not having such isolation which a personalized bare metal or self-managed cluster would have. If there is such industries of financial or other like military, there would be opting for self-managed clusters, which is like having a personalized data center to manage their own database or activities. Whereas for professional or business needs, it is managed or AWS EKS, which is still secure and it is much more like automated by cloud providers. So that is it for the video today. Thanks so much for watching. Do let me know if you have any questions or anything in the comments. Thanks. Have a great day. Bye.